Before that, before I actually began my career as a programmer, I was in graduate school trying to write a PhD thesis in computer vision. And when you're trying to do research, you have to publish it. If you cannot publish papers, right? If you cannot give talks, you will have no academic career. You better quit. So that's what I've done. But when you do research, you have to read papers, and paper has, okay, this is my contribution, and it's based on these previously written results. So all you do all day long, you read a paper, and you're like, oh, I don't understand this. So you go to the reference, and you're like, oh, I have to go to the library, find this, read it, and that paper probably has other references. So you do it all the time, and it becomes really, really annoying. So 30 years ago, a contractor researcher at CERN, he thought, okay, I'm sick and tired of going to the library. Why can't computers show me the paper, and then if I want to read another paper right there, I just click on it, and it goes, fetches that, and shows me that paper. And so his name was Tim Berners-Lee, and he submitted a proposal, right? And his boss replied, vague but exciting. So this is the highest I aim for now for my projects. Vague but exciting. So Tim Berners-Lee goes back and he implements the system that consists of several parts. You need a viewer, something that we call the browser. So this is the very first browser for HTML documents. He actually had edit button on top of view button because it's like starting a library when there are no books. You have to write a book first if you want to read it. So he had to come up with HTML, language for markup, for references, for links. And then he had to write a viewer, and he had to write a protocol for the viewer to ask for documents. And then a couple of iterations later, first World Wide Web website was born, and it kind of looks like what we use today, 30 years later. His specification for how the browser will ask the server for HTML documents is less than 2 pages. 650 words, I believe, right? Less than 4,000 characters. That's it. That's the whole specification originally. It only has 4 parts, right? It has the connection, the request, the response, and disconnection. You don't need anything else. Oh. Okay. Now, many people ask, like, why did he pick port 80? There is no special meaning. It was a port that wasn't used for any other service already, and it's kind of a nice round number. So 80 it is. Once you send the document, you disconnect. Simple. You can only get text documents. You can only get something, right? You only send back a text response, and at that time, it was only ASCII text, right? You could not send binary. You could not do anything else. There are no response codes yet. If a server cannot find a document, it will just send you text, cannot find document, and you, the human viewer, will like, oh, yeah, okay, my link is wrong. What else? No cookies, no server state, nothing. Very simple. Classic principle that I pronounce Yagni or Yagnai. You're not going to need it. Don't overthink it. Just release something. You're going to improve it later. And what does that protocol solve, right? You have to think of everything as solving a need. So what does it solve? I'm reading this document, this HTML, and I see this link, this reference that I want to read next. So I click on that, and somehow I need to get it. So we're thinking of our browser kind of doing this thing where it goes to the server and then gets the document and then shows it to you. In reality, it doesn't work like that, right? In reality, you ask Transport Control Protocol under HTTP, hey, give me this document. That goes to Internet Protocol that says, this document comes from this domain, so I need to find IP address so I can actually find the server. It goes into the cloud, and then on our side, it comes out onto the server. And the server goes back to TCP IP and sends you back. So the TCP controls how to actually send the document, how to take this long text, split it up into chunks, send the chunks, and then reconstruct so the browser can show it to you as a single logical text. IP is responsible for how to get there. It's like Google Maps of internet. Okay, so the worst part of HTTP, or the best part, depending on how you look at that, is it says you have to be backwards compatible. Imagine, let's say, how old is Athens? Like 3,000 years old. The very original document of Athens would say, whatever you build, a time traveler from today should be able to come and just live like you used to live, right? That would be unbelievable hard, right, to keep building. Okay, 30 years later, think of the progress we made with World Wide Web. Think of the first airplane and the airplane 30 years later. It would look like this, right? It would still be absolutely no way I'm getting on this airplane. But the World Wide Web became this modern superpower. All our jobs depend on it. Okay, why did it happen? Every year, the number of websites was increasing by a factor of 10. It was exploding. It went from CERN and other universities all around the world. And what did the users do? Well, the very first thing they said, I'm not interested in just text document. I need to see a cat picture. So you need to somehow send images. The very first need was for non-HTML binary data. So from you're not going to need it, we went to, yeah, we're going to need a lot. So a couple of years later, the new version of the protocol 1 came out. And from less than 2 pages, it became 60 pages. And it introduced lots of stuff. For example, how to send images. Now you have methods. You're not just getting things, you're sending things, you're asking for different things. Machine-readable status codes. Kind of important, right? User could say things so you understand how to handle it. After HTTP 1.0 came 1.1, which kind of formalized the best practices as you were using the internet more and more as more websites developed. Instead of being a single version, right, released, now everyone implements it. It went through drafts. So some websites or devices or like libraries could implement this protocol, but draft like 1, 2, and so on. And it went through a lot of drafts. And it concentrated on things like performance, like how to specify caching for resources, how to do security, because people started buying things over internet, and it became crazy. How to use, internet when we are running out of IP addresses, and the same server has to serve multiple domains. It still is the same internet as originally developed. I'm reading HTML document, I want to read this, and I'm going to the server, I'm getting the thing, and when connection is terminated, and I'm reading the new document. And we have this idea, but it kind of works. That behind this kind of electrical box, there is a cover, and all the complexity is there, and it's nice and clean, and in reality, it looks something like this. Different protocols, different devices, different libraries, and bugs, all around in this complex mess. The best resource to learn about this in real-world examples is to read this book, Tangled Web. It's a little out of date, but once you read it, you'll be surprised how anything works. How do we even keep our jobs? It's unbelievable mess. Every time I open my browser, I'm being attacked by hackers, by people trying to steal my private information, my money. So a lot of stuff, what you see, like if you ask for github.com, right, you get this unbelievable number of information going in and back. And majority of it is how to cache things, how to control access, security headers, cookies, a lot of crap for each request. And excuse me, if you look at number of requests, it takes to actually load a single page nowadays, right? It's like tens, hundreds, right? And each one sends those cookies, those headers, and so on. Okay, so once people realize I can show static pages, they realize, wait, if I want to show more data, I have to reload the whole page. So Ajax was born, and it was born kind of in the first attempt, right? First, iframes came along when one page could include another page, but that was not good enough, right? because it still is kind of limited. But from Microsoft came an extension of this XML HTTP request object. And that allowed you static page through the use of JavaScript, because before everything was just HTML, static declarative language. Now you could programmatically say, do something and then show the result. So first it was a plugin, and then it exploded, right? When people saw Gmail, right? When people saw, oh wait, it's my desktop email application, but running in a page, and it fetches data, I can send things. What kind of dark magic is this? And so what do we have now, right? On top of Ajax, we're building now new protocols like REST and GraphQL that fetch data, upload data, do everything. It still is the same HTTP, still the same TCP stack, and then IP, and then the cloud. So today, we have this thing where we can communicate with the server. We can request document, request data, send data. We also have other things, like WebSockets for real-time communication. We have WebRTC where clients can communicate with each other, not just with the server. And with the server, you have this weird thing now called service workers. And the service workers are absolutely amazing thing. They kind of blur the line where the browser ends and the server begins. And they were solving a need that was shown in the real world. Every time you use a website, if the server is down, what happens? Right? You see this picture and you're like, well, I guess I'll wait an hour and I'll reload the page. And it's not a good experience, is it? Nobody wants to see this while they're trying to use email. And so people try to solve this problem of server going down by using caching. And the caching, you say, I want to cache the page, I want to cache these resources. Turns out, like declaring, just like in static text, how you're going to cache and fallbacks is really, really hard and leads to like weird issues, and you have no power to really do what was needed. And so they decided to apply the solution that became super common in our modern World Wide Web, use JavaScript for everything. Something goes wrong, use more JavaScript. So what we decided, okay, you take your page, it already has JavaScript. You have maybe web workers, they have their own JavaScript. Introduce a service worker, which is like a proxy that runs in a browser that runs JavaScript. And so every time a browser is requesting anything, a page itself, resources, other JavaScript, Ajax, anything, it goes through this proxy where you can decide, okay, what do I want to do with it? I can go to the server. The server will send something, and here I can store it in a cache, maybe change it, and then return back to the page. From the point of a page, it looks like everything is like communicating with the server. It doesn't know that there is this layer in between of programmable logic. So anytime you want to cache something nowadays and implement offline, you go for service worker. I think that's the main use, but you can also do other things. Now, here's the problem. If a malicious user can load their own service worker, all of a sudden they see everything. Every request goes through service worker. And so you try to remove it, and then the service worker can just include it itself back, right, when you load the page again. It's very hard to get rid of malicious service worker. So please protect yourself. And that's why, for example, the service worker and everything we're discussing today doesn't work on plain HTTP sites. They need HTTPS. They need this security, where you're really loading what you think you're loading, but you're really communicating with the server you think you're communicating, and not with malicious attacker intercepting everything. So everything depends on HTTPS nowadays. And you used to have to pay for HTTPS, right? And when this, I don't know, like group of volunteers came and said, we're going to give free SSL certificates for everyone. And then the whole world like switched, and now every domain provider where you buy domain says, yeah, we also will give you free. Turns out it's not, doesn't cost us much. We'll give you a free HTTPS on top of everything. Okay, everything is good, we are secure, but we have a problem. When we connect from the browser to the server, now we have to do round trips to create a secure connection first before we send anything, and that adds time for every connection. Because remember, HTTP disconnects. So the web today, I call it today, actually more accurate would be the web yesterday. We need to make the web faster. But our problems is that even loading times.com, which is like a modern, real-time, graphical web application, not a static newspaper anymore, requires more than 200 separate requests. It's a long way from like initial idea, static page, and that's it. So HTTP1 doesn't address these issues. How do you load 200 requests? Well, each one has to create a TLS connection. Each one has to go to the server. How do you maybe load some resources first? Because you don't need all 200 resources to show times.com, right? You need some first, probably, and others are less important. And how do you avoid all this? Remember cookies and response headers and request headers? How do you avoid sending them every time? Because it's a big chunk of information. So it turns out our modern websites are not limited by the bandwidth, how many gigabytes we can upload a second. Our modern websites are really limited by how long it takes to go and fetch things, especially on mobile. On mobile, you have 5G, but if each request takes 200 milliseconds, well, those 5G are doing nothing. Okay, so that's why smart people decided we see the performance problems and we're going to implement something called Speedy. And so it started at Google, became a standard. And it rewrote the HTTP part. Instead of having a text request and response, they decided, okay, we're going to have a binary, data frames, almost like cardboard boxes. Everything, request cookies, response cookies, the data we're sending, the data we're receiving, will just go into these little binary boxes, and you have a big chunk, you're going to split it up, and everything will be like container shipping. Everything. And instead of having one connection for each request, we're going to have a single connection, and we're going to send different requests and responses on that single shared connection, because now we're all boxes. So you have like this conveyor of different requests, all going through a single connection, so you don't have to pay the overhead. You can specify which resources are more important than others. You can say, okay, resource A, give it 3 times the number of slots in that connection than request B. So you load it faster. And then load those resources. And then load D. And then once you load D, load C. And then, specify A and B. And all these cookies that I've shown that are extremely large, that go with each request, you can now compress it. Instead of sending, user agent, refer, accept encoding, like in text, you just say, user agent will be header number 1. Just send 1 instead of sending the string, so you compress them. And even better, you can say, if you're sending multiple requests to the same origin, instead of sending cookies again and again, just say, it's the same cookies, but maybe a few changed ones. So you don't send all this extra information. It changed performance practices, how we code the websites. Okay, it did not completely change it, right? You still have to use, for example, content distribution network. You still have to optimize images, but for example, some of the practices they change. For example, you no longer have to do like domain sharding just to get around the number of parallel requests. You don't have to bundle things because there is a single connection. So you can still send much of the data separately. I say, don't listen to me. Don't read the books, because the advice you probably got maybe 2 years ago is already obsolete. The best advice I can tell you about performance is measure before and after a change. Because you probably will surprise yourself. What you think is the best practice is probably not the best practice as it stands today. Now, really, the web today. Okay, Greek myth reference, Achilles heel, a weak spot of HTTP2. Turns out, when you use real-world scenarios, packets are lost all the time. Unfortunately, if a packet on a single connection that sends multiple data frames is lost, TCP says, hey, everyone, hold on. Let me go back, fetch that packet, because I promised to give you all packets in order. I cannot change that. I'm TCP, that's how I am. That's how I roll. So TCP became a bottleneck. Performance of HTTP2, even if you have like 1% loss or 2% packet loss, became worse in real world than HTTP1. So, problem. Okay, so we have our stack. We have HTTP on top of TCP, and TCP is a problem. So what do? We go back to the alternatives to the TCP. And there's only one alternative called UDP, User Datagram Protocol. That protocol doesn't guarantee delivery, doesn't guarantee order. It's like best effort. Yeah, I'll try, but I'm busy, I'm swamped here. And so Quick became a protocol that implements HTTP, but it says, okay, if you lose a packet or datagram for me, I'm gonna go and ask for it again, and I'm gonna put them all in order because I no longer can rely on TCP. Okay, question from the audience. Why can't we write a new third protocol, TCP, UDP, HTTP protocol, like on that level? It's impossible. These protocols, TCP and UDP, are implemented by probably billions of devices, proxies, switches, routers, servers, libraries in every language, everything. Introducing a third core protocol in a modern web already deployed is impossible. It's like saying, we're going to replace Acropolis with a skyscraper, and Acropolis will be on top of a skyscraper. Not going to be done. So you have to use what you have already. So Quick is like binary HTTP protocol like Speedy, but using UDP. The good thing is that while Speedy was becoming a standard, Quick was already in development because these performance problems were obvious. And so it became a new HTTP standard. Now, I've done this presentation a couple times over the years. And I used to show this slide, and it was all red. No one implemented HTTP3. Like Nginx had no plans at some point. Now, all green. 75% of clients support HTTP3. 25% of the biggest sites already use it. You're using today, and you don't even know it. Okay, I want to finish with a conclusion, right? Every version of HTTP that I've shown today was created to solve a particular problem, and that problem was not obvious when they were designing it. It only became obvious when people, lots of around the world, started using it, right? And hitting the limitation. So, original version solved the problem of loading text documents. HTTP1, explosion of World Wide Web, and loading everything. Ajax, loading data without reloading the full page. WebSockets, real-time communication. Service worker, we need to cache things, so when things go bad offline, it still works. HTTP2 was solving specifically the performance problems of HTTP1, and Quick and HTTP3 now, they're solving the performance problems that were shown by HTTP2 in the real world. I have news for you. HTTP3 future, or like the future of HTTP, if I can kind of bet, I think that in a couple of years, we'll see a new generation of HTTP2, or HTTP protocol, and it will solve the problems that only now are becoming apparent. Only the failed products that no one uses stay unchanged forever. Thank you. You've been great. I'm Gleb Bahmutov. Talk to you later. Thank you.